So last time we introduced the Fourier series. We talked about how signals can be composed of sinusoids, and we looked at some continuous time examples through that Mathematica demo, where we saw some simple functions that could be represented as sinusoids. Let's start by now looking at a discrete time signal, an actual captured sound signal, and show how the same thing can be done in that case. So here I have a simple sound. I'll play to you. Didn't hear anything. Let's see. Okay. Here's just a voice. All right. Now, the demo reads in a short segment of that sound, and that's plotted here. So this is just a brief time interval showing a few of the periods of the pitch. All right. As you might expect, this signal is very periodic. Voices are. So these are roughly the same thing is happening during each of these cycles, but not exactly, as you can see. And here, what we're going to do is we're going to try, with that green line, we're going to try to approximate that sampled signal, this blue, using sinusoids. So currently I'm using, so I can specify how many sinusoids starting from the frequency, the period associated with this entire window length. By window length, I mean the length of time of the data that's sampled. Now, I say this is discrete time because, as you're aware and you've been doing in your labs, you know that this is actually just a sequence of numbers. If I zoomed in, it would just be numbers connected with a line, right? So this represents a signal that's been sampled in time at a certain frequency. Okay, so if I can specify here in a variable k how many sinusoids I want to use for the approximation. Right now it's just 2. So it's only using a sinusoid of the period of this entire window and the next multiple, so the one that has 2 cycles during this window. And as you see in this plot, whoops, wrong one. Okay, as you see, the green approximation is very bad. It looks like it's not doing anything. Why don't we have a stronger sinusoid there? I've asked for 2 sinusoids. It doesn't look like it's doing much of anything. Any ideas? Exactly. I mean, this signal doesn't go up in the second half and down in the first or anything like that. There's nothing really happening at that frequency. So the best approximation is pretty much 0 for those low frequencies. If I can do this for 3, see how much better it gets. Okay. Still, let me move these over here. Okay, still not much. How high do you think I have to go to get something? 5? Does everyone agree? You think I'll get something at 5? Okay. Let's try it. Oh, I did get something. Nice. In fact, I could have gone to 4 and gotten something. Let me show that. Why is 4 the right one? So I get pretty much the same thing as 4 as I get at 5. Why is that? Yes? Yeah, it's exactly. I have like four periods represented in this sample, right? So sinusoid of that same frequency should capture something. All right. So over here what I'm showing is I have 2 other things. This is just showing the most recent sinusoid, the last one I asked for, the 4th one, showing what it is. Of course, the 4th one is pretty much the whole thing at this point. And this shows a different representation of these sinusoids. Rather than plotting them in time, it simply gives the scaling constant that we assign to each sinusoid, and it gives the shift, the time shift. Okay, so it would be more appropriate to show a phase shift, which is like a time shift scaled properly. But anyway, so these values are showing what coefficients I used to do this reconstruction. Okay. And we see that they're basically 0 until we get to that 4th sinusoid, and then it's non-zero. So if I go to 5, or let's go to Let's jump a little bit here. Let's try 7. Still not much has changed, and this is why. Look at these coefficients. They're pretty much 0 for 5, 6, and 7. But once I get up to 8, you might expect I'm going to see something interesting again. Okay, so now I have something non-zero. I'm not sure what that little line is. Oh, I know. This is showing the change. The thin line is showing the reconstruction up to 7, and then the thick line is including 8. Okay, this is showing the 8th sinusoid by itself, and this is showing all the coefficients. You see 8 was big again, and it's because it's actually a multiple of that frequency 4. Okay, so it's starting to get interesting. Still not a great approximation of the blue, but we can go up to a large number now. Let's go up to like 30 and see how good the approximation is. Okay, that's looking pretty good. You see it has some errors in this region, but it tracks the signal pretty well. This is using these coefficients for the sinusoids. Now, if this were perfectly periodic, we would actually get exactly 0 between all the multiples of 4 here. But we see it's not exactly periodic, and maybe even the period, maybe this isn't exactly 4 lengths anyway. Maybe it's close to 4. And because of both of those reasons, we get at least, especially in the high frequencies, non-zero values in between the multiples of 4. It starts looking less organized out here. Okay. Now let me go to, let's say, 50. Oops, not 350. What did I do? Okay, now it looks like it very much matches the original data. All right. And here we see something interesting. The high coefficients now are pretty much gone. Okay, so that once we've matched it very well, there's not much more that's needed. So all the coefficients from here on out will be very small. So we might say that we've basically captured the signal in the first 40 coefficients. Right? All right. In fact, if we went up to a high enough, so the Fourier series, we said, takes an infinite number of sinusoids, potentially an infinite number, to exactly reconstruct any signal you want. But in discrete time, you don't need an infinite number. So if we went up, if I counted how many samples I have here, and if I went up to half that many sinusoids, I would exactly reconstruct it in discrete time. Okay, so it's a little different than continuous time. We don't need to do this forever. 50 is not enough, but if we went to whatever, I don't know how many are in here. I could check. What is it? What are we calling that thing? Duration. Okay, so we have 1,500 samples. If you divide that by 2, that's how many sinusoids you would need to exactly get it. I mean, maybe less, but you would, if you had that many, you would for sure reconstruct this signal. Okay. Good. So. Why is that the, or actually you should maybe say the maximum. Why is that the maximum? Well, we'll see. Maybe we'll get to it in this lecture, some explanation of how you can, how many different vectors you would need to represent any arbitrary vector. Okay, and that's basically how you can think of this. Yes? Oh, it was 4 because if we go back here and take a look, you can, if you, this we said is roughly repeating. Let's say there are these, it's repeating, looks to be roughly periodic with this period interval, and this is 1/4 of the total length of our signal here. Since I'm trying to match this using sinusoids starting with a fundamental frequency that matches this window, then the 4th harmonic, the 4th multiple of that will be the one that matches the period of this actual data. Okay. Okay. So we should start by looking at some definitions of energy and power. Let's do it this way. And we would define the energy of a signal, let's say it's continuous time. We'll also have a discrete time formula. Okay, the energy is the integral of the absolute value squared, or the magnitude squared, of x integrated over its entire negative infinity to infinity, the entire domain. All right. So we call that the energy. And you can think of this, why would we call such a thing energy? Well, it's nice that it's non-negative because we squared it. But some examples where this would actually relate to energy, imagine that x of t is like a current in a circuit. And this would be the energy dissipated, or proportional at least, to the energy dissipated in a resistor. Okay? Because if you know circuits, you can calculate power by multiplying voltage times current times the resistance, and just voltage times current, sorry. Of course, through a resistor, they're proportional. So you could write this as either the current squared times the resistance, or the voltage squared divided by the resistance. So anyway, they're proportional to the square of the value of either current or voltage in a resistive circuit. If x of t is, let's say, speed of a moving object that has viscous friction, so it has friction that's proportional to its speed, okay, then you can look at power is work divide, the rate of expending work. The force would be proportional to the speed, but also the distance is proportional to the speed. So you get a speed squared when you calculate the instantaneous power in that situation. And there are many situations where the square of the value is related to some sort of energy or power. I've related these both to power, and yet I'm saying energy. Well, that's because we've integrated over all infinity to get energy. Okay. So we don't worry about the units. We're not worrying about what's the constant times this squared. We just say that the energy of a signal is this formula. The power, then, there's an instantaneous power, which is just a time-varying function. It would just be this thing inside here. That's sort of an instantaneous power. You integrate it to get energy. But when we say power, we actually mean time average. So it would be the limit as t goes to infinity of this energy integrated over an interval. So we're just looking at the average power here. Okay, so that would be the average power. Now, usually when we care about power, it will be for a periodic signal. Okay, that's the only time we're going to care about it, because the signals that are not periodic that we look at are going to be ones that decay in time off plus and minus infinity. So they wouldn't have an average power that was non-zero. But a periodic signal would. So it's important to know that you don't have to be afraid of this limit, because if it's periodic, then 1 period is sufficient for this integral. So in other words, for a periodic signal with period cap t, then you just do one of these. Integrate from 0 to t. And that's going to equal the limit, okay, where t is a period. Okay. In discrete time, we have the same thing, but as you'll see over and over, we're just going to replace integrals with sums to get our discrete time formulas. So here we just sum the magnitude squared for the energy, and the power as the same limit, n to infinity. And same thing, if you have a period, then you can just integrate over 1 period. Okay, well, that's a period. All right, any questions about that? I'll put a note here that x of t, this thing here, is instantaneous power. Okay, so we should do a quick example. Example here would be, let's say x of t is just sine of t. And we want to know what's the energy, what's the power of this. Okay, what is the energy of this signal? That one we can do maybe in your head. Any ideas? All right. It's infinity. We'll see that in a minute if you don't believe me. But the energy is infinity. That's going to be the case for any periodic signal except 0. Okay. So we aren't actually interested in the energy of periodic signals. We'll see later some non-periodic signals where we do care about the energy. Okay. But for a signal, you either care, sometimes they're categorized as an energy signal or a power signal, and I might use that categorization as well. And we would say it's an energy signal if the power is 0, but the energy is, well, if the power is 0, then maybe we'll call it an energy signal because it might have a finite energy. We'll call it a power signal if the energy is infinite. Okay. So this is a power signal, which will be the case for all periodic things. So let's say, what is the power? Okay, we can calculate that now. And we just need to look over one period, right? 1 over 2 pi, the integral from, what am I using here? Negative pi to pi? 0 to 2 pi. Let's do that. Sine squared. T. Sine's real, so I don't need to worry about taking magnitudes. And what we want to do this integral is just replace sine squared with our trig identity, which is that that's 1/2 1 minus cosine of 2t. And cosine is periodic with about 0. So integrating cosine over one period, as you would expect, is 0. So really, it's just an integral of 1 over a period of 2 pi. That 2 pi cancels that one. We get a half. Okay. So the power of sine of t is a half. Now, this may ring a bell because in circuits you have this notion of AC. If you're using AC power, AC power supply, then you convert voltages to RMS voltages. And the conversion is simply that you say that you take the peak power, the peak voltage, and you divide it by square root of 2, and you call that the root mean square voltage. And the reason is that if you do that conversion, you can just plug in your RMS voltage into all of the same formulas you would have had for power dissipation. And notice that the formulas always involve the voltage squared, and that voltage squared is going to be the peak voltage squared over 2 because we've squared that square root. And that 1 over 2 factor, the purpose of that is exactly what we just derived. That even though sine goes up to a voltage of, goes up to a magnitude of 1 at its peak, the power is a half. Okay. So now let's define a notion of inner product. And to begin with, let's talk about the inner product that you've seen before. And that is that if x and y are vectors, then the inner product is just, we can denote it this way, these brackets, but it's just x transpose y. All right. This is part of linear algebra. You might call this the dot product. And what it means, because I don't require that you've all studied linear algebra. That's fine. What this means with the transpose is that you just take all the values in your vector x, multiply each one by the corresponding value in y, and then add up all of those products. That's what the dot product is. Now, we are going to keep things general. Our x and y could be complex. And then the definition of inner product actually has a conjugate on the second one. So if they were real, that wouldn't matter. But in general, you put a conjugate. Okay, but let's extend that because, in fact, inner products are not defined only for linear algebra. They're not defined only in this Euclidean space. There's a general definition of inner product. It has to satisfy a certain set of rules. And here are some valid inner products. If x and y are signals, then for continuous time, we'll say the inner product between them is the integral from negative infinity to infinity of x, y conjugate. You can see the similarity here between the above one. We multiply corresponding values, sum them up. It's an integral instead of a sum. In discrete time, it's actually a sum. So if they're discrete time signals, then we would sum. And then it's really the same thing as considering these infinite length vectors. All right, we were going to define one more inner product because, like I said, there's not just one definition of an inner product, even for the same set of, the same domain. So if x and y are periodic, then we'll use another, let's say both with the same period, with period t, or n. I like to use capital N for the period in discrete time. Okay, then the inner product, and here we'll denote, put a little, the period next to it to know this is a different inner product than the one I defined above. Okay, here you just integrate over one period and you divide by t. So it's like an average type of thing. Whoops, not infinity. Discrete time, same thing. If I go fast enough in this lecture, we'll get to actually use these inner products to explain where these Fourier series equations come from. That might end up next time if I'm too slow. But all right, so notice a couple of things that we now can interpret energy and power in terms of these inner products. So energy, as we defined above, is the inner product of a signal with itself. All right. And generally, when you take an inner product with yourself, people call that a norm. So this is like the norm of x squared. Okay. So, and then we also can notice that our formula for power is just this periodic inner product of x with itself, assuming it was periodic. Okay, if we wanted to call that a norm, I won't be using this in this class, but maybe we would put a parentheses t down here to indicate this was a periodic norm, not the regular norm. Okay, the reason for the parentheses is there's already a notation of a norm with a little number next to it. That comes from math, and that's not what we mean here. Okay. So now that we have inner products defined, we can define a notion of an orthogonal set of signals and an orthonormal set. All right. Before we go on, I wanted to note one thing here. Something interesting about discrete time periodic signals. We defined a periodic signal, but we kind of only gave examples of continuous time. I drew pictures of continuous time signals. Of course, the same definition holds for discrete time. A period should be one where, it equals itself one period away. But discrete time signals are only defined at the integers. Okay, so necessarily, the period of a discrete time signal must be an integer. And because of that, you have situations that you might not have expected. You might say, let's look at a very simple signal, sine of n. And what's the period of this? So we've seen sinusoids in continuous time, and we know they're always periodic. Here's a discrete time sinusoid. What's the period? What? Infinite, meaning it's not periodic. This is not periodic because if it were a continuous time signal, well, the period would be what, 1 over, it would be 1 over 2 pi? No. Yeah, it'd be 2 pi. So, but the problem is 2 pi is not rational. So, every multiple of that is a period in continuous time. But none of those are going to be integers, no matter how far you look out. Okay, so this is actually not periodic, and you can't say, well, am I just playing games because, it does have a period of 2 pi? Well, it actually doesn't, because it's not even defined between the integers. Although I've expressed it as sine n, you should have no belief that it actually follows sine n between the integers, right? So it doesn't even make sense to ask for its value at 2 pi. All right. Let's do this. Okay. So we have this notion of a set of signals being orthogonal. And so what we mean by that is, if you have a bunch of signals, you think of these each as functions, but actually this works for any inner products. They're orthogonal if the inner product between any two of them, I and j, equals 0 for all I not equal to j. So any two of them have a 0 inner product. All right, and we say that they're orthonormal if they're both orthogonal to begin with, and when you take the inner product with yourself, that equals 1 for all I. Okay? So another way of saying a set is orthonormal is that the inner product between any two, I and j, equals the indicator function that I equals j. This is just, you've seen this in your homework, this is just 1 if I equals j, 0 if I doesn't equal j. Okay, so that's what it means to be an orthonormal set. It's just orthogonal, but you've also normalized each one. You can normalize by just scaling them to make their norm equal 1. All right, let's get back to our Fourier series definition. Now, yes? Yes. Yeah, we would only talk, exactly. We'd only do that periodic inner product if they have the same period. Otherwise, we wouldn't try to do it. Yeah, exactly. Okay. So suppose that ck equals, so this is the formula I gave last time for the Fourier series. I said that the coefficients of, you can get a set of coefficients associated with any periodic signal under this computation here. And from that set of coefficients, you could then reconstruct x of t as the sum of complex exponentials with those coefficients as their weights. All right. We only gave the continuous time version last time. You have also discrete time definition, which I'll give right next. So this was continuous time. we gave names to these. The top one is sort of the forward transform. The bottom one's the backwards, and they call that analysis is the first one, and synthesis is the second. So here, what we have is that I should have said, to begin with, we're only doing the Fourier series. We assume we're doing it for periodic signals, or you'll see we could do it for signals of a finite duration. Same thing. So assume that x of t has period t. Okay, then we could use this formula. In discrete time, assume x of n has period n. All right. Then the formula is very similar. Just replace that first integral with a sum over one period. Now you probably noticed that when I sum over one period, I go 0 to n minus 1, not 0 to n. If I went 0 to n, remember the value at n equals the value at 0 by the definition of being periodic. So that would be repeating the same value twice. Don't do that. And to reconstruct, you have, this is almost identical. There's one difference here. And I'll let one of you notice what's the difference between yes. Yes, I should do something like that. K equals okay. What's the difference between these two formulas for reconstructing? So as I mentioned when we were looking at the voice data, that a discrete time signal, you actually don't need to sum an infinite number. We'll see this soon. We'll understand why this is happening. Turns out it's redundant to go beyond the nth term here. So here we went, up above, we went from negative infinity to infinity in our sum to reconstruct a continuous time signal. For discrete time signals, you don't have to. In fact, you don't. You shouldn't. You just do n of them. Okay? And you'll get back the signal exactly. Okay, so I want to become a little more familiar with this, especially to think about what are these complex exponentials that we're using here. Okay, what are these things? Also, I want you to notice how the forward and backward equations are so similar to each other. I mean, if you compare them, especially in discrete time, here you've got an integral. For continuous time, you have an integral and a sum, so that's one difference. In discrete time, they're both sums. And really, the only difference here is there's a negative in the exponent of the first one and not a negative in the next. And we'll like that sort. That sort of duality is going to be very nice in terms of understanding properties of the Fourier transform and Fourier series. Okay. So what does each of these look like? I mean, we have Euler's identity to understand e to the I something. But let's just try to get some more intuition about it, because after all, we're using these to compose our signal. We say that that's useful somehow, right? First of all, realize that a complex exponential is living, if we think about the complex plane, and here's the 1 and here's the I. Complex exponential function, this term right here, this term here, what's the magnitude? It's 1. It's always magnitude 1. So here's a circle of magnitude 1. It's a unit circle. We know that the value is always somewhere there. And in fact, the phase, the number up here, is simply saying how far around that circle you are. Right? So if we look at something as simple as, let's take one of these guys down here. So e to the I, let's say 2 pi, and forget about the k and the t, I'll just call that f. T. as time evolves here, when time is 0, the value is right here. Okay, that's e to the 0. And as time goes on, it moves around the circle. And at what point in time does it make a complete rotation? Well, that's what this f tells us. Okay, so the f is the frequency with which it goes around this circle. All right, so 1 over f would be the amount of time it takes to go around this circle. So that's how you should think of these signals. They have a real part and an imaginary part. Remember, in the complex plane, this is the real part. And so when you're thinking about it in Euler's identity, you're splitting it up into its two directions. And of course, if you watch something go in a circle from the side, it's a sinusoid, right? It's a cosine. And if you watch it from the other side, it's also a sinusoid, but it's got a phase shift, and it becomes a sine, all right? And so if you have a cosine and a sine together, working together, they make a circle. So just imagine these things as circles in the complex plane. Here's a visualization that might help. So this is a three-dimensional plot of, here we have e to the I pi t. Okay. It's three-dimensional. How is it three-dimensional? Well, t is going along horizontally. Okay, so this is t. And what we have is that vertically, let's see, in this case it's, oh yeah, okay, vertically we have the real part, and coming in and out of the page we have the imaginary part of the value of this function. So it requires 2 dimensions to plot the value of the function. All right, and we can see it's a little distorted because it's giving us perspective, but this is a coil. Let me try to rotate it. That'll help. Okay, so this is the function. This is what all complex exponentials look like. Of course, the coefficient up here, the frequency, is just going to say how fast the coil is wound, right? The magnitude's always 1. Okay, what would happen if I made the frequency negative? How would that change anything? Yeah, it would go around the circle the other way. So there is a difference between a positive frequency and a negative frequency when we're talking about complex exponentials. Okay, they both have the same frequency, but they're going in opposite directions. I could do that here, but I'm afraid to just mess everything. Oh, let's see. Okay, it goes the other way. All right. So just have those in your head as what we're using to compose our signals. This is what the Fourier series is giving us. The shifts and scaling of these things. You can see that these have a nice property. If you multiply them by a real number, they get bigger or smaller. If you multiply them by something that has like a complex number, the magnitude scales it, but the phase will do something nice. When you change the phase, you rotate it. But rotating a coil is the same as time shifting a coil, right? So even though the phase is rotating this thing, you can equally well think of it as being a time shift. Okay, so if our signals are actually real that we want to analyze usually, how can we even construct a real function from these guys? Remember that a real signal, its domain is t, let's say, and it's real, so it only lives in the vertical plane of this plot, okay? Because the vertical plane is the real part of the signal value. So a real signal just lives in the vertical plane. How can we create that by adding together a bunch of coils that pop out of that plane? We could take the real part, but actually the formula for the Fourier series doesn't say take the real part. It says just add these up and you get back your signal. Yeah. We could do a projection, but still that's not a part of the formula, right? Because the formula just says do this sum. These are each complex exponentials. You're going to get back your signal. Okay, so what's actually happening is if you take positive coils with positive frequencies and the right coil with a negative frequency and you add them, you can get the imaginary parts to cancel, right? And that's what's going to happen. That's why you can construct a real signal even though these are each complex. because you can add together a positive frequency and a negative frequency just right to cancel the imaginary parts. That's exactly what Euler's formula says. Okay, so that's what we'll be doing, and it may seem like extra work. Why go into the complex domain? Why decompose it into these complex functions when all you really care is the real parts? But it's because it simplifies everything. We could do everything in sinusoids and be stuck with a bunch of messy trigonometry, or we could do everything this way, and actually it simplifies the properties, it simplifies the math, it does a lot for us. Okay, all right, that's enough about that. So let's now, boy, we don't have much time. So I'm not going to be able to derive these formulas. We'll do that next time. But I'm going to introduce some other notions of transforms. My main purpose here, these aren't going to be transforms that we study. We're going to study Fourier. My point here is just to give you the concept of a transform, and that this isn't the only one. There's many ideas of transforming a signal into a different representation. Okay, to start with, let's do one that you are familiar with. So there's a transform where you can take x of t, basically the idea of any transform, you somehow represent it with a different set of parameters. In this case, I'm going to represent it with a set of numbers, a1, I want to start with a0, and one other number, which I'll call t naught. And the idea is that once I transform x into this list of numbers, I should be able to undo it and get back to x. That's the main idea of most transforms. It should capture the information. Okay, for this one, I want you to guess what the transform is. I'm going to give you the formula. You calculate x of the reverse formula to go back is x of t equals a naught plus a1 t minus t naught plus a2. So this formula, this type of transform is going to, I want to compose x in terms of a sum of these polynomials. Does this look familiar? I'm doing this sort of as a puzzle. You know what it is. What? Taylor series. Okay, so this, and it's the Taylor series about t naught. And so then, because we know it's a Taylor series, we know how to even calculate those coefficients, right? So to calculate those coefficients, you would do ak equals 1 over k factorial. The kth derivative of x of t evaluated at t naught. Right? So that's how you calculate the a's. You use derivatives, and then you can reconstruct your x. Now, this transform, this Taylor series, isn't guaranteed to work for every function. It works for analytic functions. That's the name given to the types of smooth functions for which this will work. So for analytic implies smooth. As an example, we can come up with a simple function for which the Taylor series transform, this expansion, doesn't get back your signal. So it doesn't work for this type of thing. So let's say you have x of t equals t squared for t less than or equal to 0 and 0 for t greater than 0. Okay. Then, of course, this is not analytic. If you did a Taylor series expansion here, well, you would use that t squared, and you would get back, when you invert this, you'd get quadratic function as your Taylor series expansion, even if you took infinite number of terms, right? And if you did it over on the other side, you'd just get back a constant, no matter how many terms you took. So it doesn't work for every function, but that's okay. You can have a specified class of functions for which a transform works. All right. Let's see, non. All right. I'm going to do 2 others, but probably not necessarily today. We'll also look briefly at the wavelet transform, and then we'll look at the Fourier transform and compare. One thing I do need to mention out of order is a property that all of the transforms that I show here, we're not going to do many, just wavelet, Fourier, Taylor, they all share a property, and I'm mentioning it because it's important for your homework. So, and that is that linearity I don't know what to say here. They may be linear. Transforms don't have to be linear, but the ones we're looking at are. And that means that if you transform, linearity simply means if x transforms to something we'll call capital X, and if y transforms to capital Y. Now remember, in the Taylor series case, these are lists of coefficients. In the Fourier series case, they're also lists of coefficients, right? And then we would have that alpha x plus y transforms to alpha, the transform of x, plus the transform of y. Okay? If that works, then your process is linear. This is a very general application. And, well, that should work for all x, y, and scalars alpha. So all constants alpha and all x and y that are signals. Okay. So this linearity, you can see that the Taylor series is linear. Why do we know that? Yeah. Of addition, yes. And we might want to also look at this formula. And is this top formula also, yeah. So everything here is linear. Yep, exactly. I guess it might be enough what you said, that because this is a linear function of the age, that should probably be enough. Yeah. And we also know derivatives are linear. So they have this property. Yeah. Oh, because you were trying to move the 1/2 over here. Yeah. Okay. So this is linear. You can also look at the Fourier series and realize that it's also linear. So that means if I took, whoops, that's not Fourier series. If I took, 2 samples of sound, the one I already played for you, the ah sound, and some other sound, and added them. By the way, what would that sound like? Well, physics adds sounds all the time. Through, its operation. So we're used to hearing sounds added together. You just hear them both, right? And if you added the 2 and took the Fourier series of the result, turns out that would be the same as calculating the Fourier series coefficients for each one separately and then just adding them. And that you can see that these functions are linear, and that's why that happens.